Alright, today's problem is search and rotated sorted array. So in this problem, they give us an array, except this array has the property that it might be sorted, but rotated around the pivot. So here you can see that 0 starts out in the middle of the array, and we wrap around the end instead. Okay, so we're given a target value to search. If we find it, return the index, otherwise -1. They give us some nice things here. For example, we can assume no duplicate exists in an array, so that gets rid of some edge cases that we have to check. And finally, they give us a hint that the runtime complexity must be in the order of O log n. So O log n is the same runtime complexity of binary search, so it seems to suggest that every iteration we're throwing away half of the array that we need to search for. Okay, so a brief refresher on binary search. If we have an array like this, 0, 1, 2, 3, 4, 5, 6, 7, we can visualize it as something that looks like this. And then in binary search, what we have is we have a beginning and we have an end. We have a window that we're searching for. So this will be our end, this will be our beginning, and we're going to probe the middle of between beginning and end. So here's the middle. And suppose the target existed on, let's say here, this is our target. Then when we compare the target's value with beginning and middle, we see that it has to exist between this line segment and not here. So that means this we can just ignore. And now we can move our end window closer. So this will become our new end. And then we can once again probe the middle. And here we might end up probing the middle here. And now instead, we know that our target must be somewhere in this segment. So you can see every time we're throwing away half the array here, throwing away half of the array there. Okay, but what's special about this problem is that our question might look something like this. So this might be, 4, 5, 1, 2, 3. Or maybe this is 3, 4, 5, 6, 1, 2. So there's this kind of a cliff that happens. So let's explore the two different cases that happens when we probe our middle. So we have our beginning here, and we have our end. And here, when we probe the middle, we land somewhere here. So here is our middle. And then on this side, we have our beginning and our end. And here, when we probe the middle, we have this as our middle. And let's figure out some easy conditions to check. So here, seems like let's see what happens if our target is here. If our target is here, we know we need to search for this area with the following inequality, right? So if middle is less than our target, less than our end, then we know it's here. Otherwise, it has to be somewhere here. This is an easier condition to check than like, if our target is bigger than beginning but less than. So it's easy, just let's go for the easy one and then make this the else clause. So this will be our if clause, and this will be our else clause. So similarly, on this side, we'll look for the easier check here. So let's assume here is our target. This has the property that beginning is less than target, less than middle. And then here will be our else clause. So all that's left to do now is to distinguish between these two cases of probing the middle. So in here, you can see that our middle is less than our beginning. That's when we know that the cliff is on the left side. And then here, if our middle is greater than the beginning, then the cliff is on this, or the cliff is on the right side, and we're in this case. Okay, so with that knowledge, let's try and code this out. Here we go. So let's have our beginning. So I'll just do b. We'll have our end, which will be length -1. And now we're in a while loop. So when do we want to stop? We want to stop when it no longer makes sense. So basically, we want to stop when beginning is greater than end. So for some reason, our indexes are reversed. So here, what we can have is while b is less than or equal to end, we want to keep doing this. We're going to form a middle, and our middle is going to be, it's a little bit hard to read. Let's just do beginning, end, And while beginning is less than or equal to end, we have middle, and it's going to be equal to the beginning plus the offset divided by 2. So however long our beginning to end is, and we get half of it, and then we offset it by the beginning. That's how we're going to get the middle. Okay, so if nums at middle is equal to our target, then we're done. We can return middle. That's the index of our target. Otherwise, we want to check the two cases. So the two cases we want to check here is this one here and this one. So let's do the first one. So if, let's see, actually, I think the second one, if nums middle is greater than or equal to nums at left. So this describes this case, nums middle greater than or equal to nums at left. Or sorry, nums at beginning. Then we want to check this case. This is the easy case to check. So if target is greater than or equal to nums at beginning, and target is less than nums at middle, then we know that it must be on the left side. So now we can shift our end to be equal to the middle minus 1. We don't just shift it to middle because we've already tested for middle, so we can do middle minus 1 for a tighter bound. Otherwise, it must be on the right side. So our beginning is going to be equal to middle plus 1. Okay, so this handles this picture here. So now we want to handle this picture on the left side. So on the left side here, we have else. The easy case that we want to check is for this ramp right here, and this is the condition. So if our target is greater than nums at middle, and target is less than or equal to nums at end. Now you notice here I use greater than, but here I use less than or equal. Reason being that greater than is because we've already checked nums at middle, so we know it must not be that. And then here, less than or equal is because we want to handle the edge case when the target is at the beginning or at the end of our window. So here it's on the right side, so we'll have beginning equals middle plus 1. Otherwise, end equals middle minus 1. Okay, and if we loop through all of this and we never return middle, that means we never found it, so we'll return -1 here. All right, let's make sure this compiles. Okay, looks good. We'll submit. Cool. Okay, let's go over the runtime a little bit. So you can see here, inside every iteration of this beginning and end, we are shifting it by half. So we're erasing half of our array. So this is very similar to a binary search. And by the end of it, if we have to go all the way to the end, then our indexes have crisscrossed. So this has a runtime of O of log n. If you want in a separate video, I can go over recurrence relations for how to actually derive this. But usually the rule is, if your input size gets smaller by half each time, then the runtime will be O of log n. Okay, that's the end of this video, and I'll see you on the next one.